Metallic compounds, or just metals, are very different from ionic and covalent in terms of the way that they bond. So, with metals, we have a very low attraction compared to other elements to those valence electrons. That's because of a low Zeph, and as we go down a row, an increased shielding. So rather than two atoms sharing electrons or two atoms exchanging electrons to make ions, we're talking about a whole bunch of atoms kind of doing the same thing. That weak attraction for electrons means that it's possible to pull 1 to 2 and sometimes even 3 or more valence electrons away from the atom, but they're not being pulled specifically to a different atom. So what happens is we've got those electrons that are somewhat freely moving or are delocalized. We use the phrase a lot, a sea of electrons, not to say that everything is always moving around, but everything is kind of surrounding our metal cations and has some ability to move freely. So our attraction here is from that core. We see the positive core, so our nucleus plus any inner shells of electrons are attracted to those valence electrons. So right here we can see each cation would be attracted to the electron would be attracted to the cation. So we actually have a fairly strong bond. Depending on the number of valence electrons that are floating around, and depending on the Zeph or the positive charge, these can be very, very, very strong, or sometimes they'll be a little bit weaker. One notable exception, and I'm scooting the wrong way here, mercury is one of the only metals that is a liquid at room temperature. That tells us something about having so much shielding in that case that the attraction between the core and those valence is fairly small. But the fact that the electrons are moving around really gives a lot of unique properties. We don't have specific things held in specific places. So that's why we can change the shape of metals, make them into wires, flatten them out, melt them down, do all of that, malleable and ductile. And the freedom of the electrons is what makes them good conductors of electricity, even in that solid state. We can have a metal that is a pure sample of metal. So it could be like a whole bunch of iron atoms. Every single one in our bond would be iron nuclei with the 2 to 3 valence electrons floating around between them. That would be metallic iron. And that would work for any of the metals, even the alkali metals. When we have a solid sample of those, not the ion, not after it's lost it, it follows this bonding pattern. Very often, we want to make a mixture of metals, or we want to take the property of multiple things and put them together to kind of change those properties slightly, or to get the best of both worlds. Anytime we have a mixture of elements held together by metallic bonds, that's called an alloy. Most of the time, it's metals with metals. Every now and then, we might sneak in a metalloid or even a few non-metals. Carbon shows up in very small amounts in some alloys. They still have to have metallic properties. They still have to kind of have that same characteristic free-moving electrons, or a sea of delocalized electrons, for it to be a metallic bond and an alloy. But we can make a substitution in that may change the ability to conduct. It may change how hard or soft the metal is, and that's why we would make alloys. If the two metals that we are mixing together are very similar in size, then we would just take our repeating pattern of cations surrounded by electrons and pop one element out, pop the other one that's similar in. That's a substitutional alloy. Zinc and copper are right behind my head there. They are right next to one another on the periodic table and very similar in size as a result. Their radii are within 15% of one another. That's generally the border there. So we're looking for two numbers pretty close to one another. You would just take out some of one element, put in the other. So zinc and copper make brass in different combinations. We have different types of brass. We can also mix in other elements, iron, cobalt, nickel, to make different combinations there of bronze or steel that are all substitutional because we've got that mixture there. Interstitial alloys, on the other hand, are, instead of the two atoms being very similar in size, you have one that's way larger or way smaller than the other. So putting the other one in kind of messes up the nice, neat pattern. So instead of just substituting, it goes into those tiny little gaps in between. So the example, and I said this previously, and I incorrectly, I was thinking of stainless steel, which still has a little bit of carbon, but those are interstitial. Big differences in size, and that makes sense. Carbon's way up here with only 2 energy levels, whereas iron is using energy level 4, a big difference. That would cause a bigger change in properties. Here, the zinc and the copper are very similar, but because the carbon and the iron are very different and the way that the atoms arrange themselves as a result are very different, we would have an alloy that still is between the two properties, but has more significant difference than something that's substitutional.